All right, so today we're looking at simplifying radicals. So before we get into it, we're just going to identify different parts of this expression here. So this sign right here, you've probably seen it before, that is our radical sign. Okay. What's underneath the radical is what we call the radicand. So the number underneath is called that radicand. And then where you see this n, that is the index. Okay, so typically our index that we will be using in Algebra 1 is a 2. So that's when we have our square root, which is probably what you're most familiar with here. Okay, so a radical expression is an expression that contains a radical sign. A radicand is the expression under the radical sign. And if there is no index written, then the index is 2, meaning to take the square root, which is what we will be doing today. And how we are going to simplify these expressions with radicals is we are going to be using a factor tree. To simplify the radical expressions or remove all perfect squares from the number. Okay, so let's talk about what perfect squares are. Okay, so a perfect square is just a number that is squared so that it can be so you can take a square root of it. So right here we have a list of numbers, and we're just going to square each of these numbers. So 1 squared, that is just 1. 2 squared, that is 4. And it's a perfect square because I can do the opposite and take the square root of 4 to get back to 2. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. And 12 squared is 144. Okay, so we can always go back to the original number by taking its square root. Okay, so now let's talk about prime factors. So prime factors are numbers that are only divisible by 1 and itself. Okay, so examples of prime numbers are 2, 3, 5, 7, 11, 13, and the list will go on. Okay, so those are your first 6 prime numbers. Okay, and each of these numbers can only be divisible by 1 or itself, or 1 and itself. Okay, so now let's look at actually simplifying radical expressions with prime factorization. And this is where we look at a prime factor tree. Okay, so we are going to create a factor tree for the radicand. And remember that radicand is the number underneath the square root. Once we create our factor tree, which we'll get into that and how that will work, we're going to identify pairs of numbers. Once we find the pairs, we will take one of those numbers and it will go outside the radical, so outside the square root, as just one number. Any numbers that don't have a pair, those leftover numbers, we're going to leave those under the radical or under the square root. And then we will simplify by multiplying the numbers outside the radical, and those will become our coefficients, and multiplying the numbers inside the radical, which is what we call the radicand. All right, so let's practice with finding a factor tree for numbers, okay, using our prime factorization. Okay, so we're going to draw a prime factorization tree for 180. So how this will work is we will start with our smallest prime number. So I'm going to rewrite those prime numbers up here. 2, 3, 5, 7, 11, ... Okay, so our very first prime number, the one you're always going to start with, is this 2. Okay, so we're going to see, can 180 be divisible by 2? And it's even, so it can. So what we're going to do is just draw 2 lines. The prime number that we're dividing by will go on the left. And then 180 divided by 2 is 90. So I'm going to put a 90 on the right. And then we're going to keep dividing by 2 until we can't. So 90 is also even. So we can divide 90 by 2. And I always put the prime number on the left. 90 divided by 2 is 45. Okay. And we keep going. 45 is not divisible by 2. So I go to the next prime number, which is 3. And so 45 can be divisible by 3. And it's 3 times 15 gets us back to 45. And then we keep going. 15 can also be divided by 3. 15 divided by 3 is 5. And 5, so that can't be divided by 3, so I go to the next prime number, which is 5. So obviously 5 can be divided by 5, and that's 5 times 1. So you're going to keep doing this until you get a 1 on the right. And that is your prime factor tree. So what you'll notice is if you were to take all the numbers on the left here, so 2, 2, 3, 3, and 5, if you were to take all of those numbers and multiply them, 2 times 2 times 3 times 3 times 5, that's going to get you back to 180. Okay? So now we're going to draw a prime factorization tree for the number under the radical, and then we're just going to circle the pairs like it had in our steps above. Okay? So just practicing that part. So with the square root of 80, we are going to first look at dividing it by our first prime factor, 2. 80 is divisible by 2, so it would be 2 times 40. 40 is also divisible by 2, so that would be 2 times 20. 20 is divisible by 2, so that would be 2 times 10. And notice I'm always putting that prime number on the left. 10 is also divisible by 2, so you keep going until you can't divide by 2 anymore. And that would be 2 times 5. And so now we're here at 5. 5 is not divisible by 2, so we go to the next prime number. 5 is not divisible by 3, so we go to the next prime number, and that would be 5. So 5 is divisible by 5. It would be 5 times 1. I got to the 1, so now I stop. Okay? So what you'll notice is if you were to multiply 2 times 2 times 2 times 2 times 5, that would get you right back to 80. Okay? And so if we were actually simplifying the square root of 80, you would need to identify the different pairs. And that's all we're going to do on this one, is just identify the pairs. Okay? So I have a pair of 2s here. And then I have another pair of 2s here. Okay? So that's what I mean is if there is a pair of prime factors. Okay. So let's look at our next page. All right, so now we're actually going to fully simplify these expressions using our prime factorization tree. Okay, so our first problem here is the square root of 24. So again, we take that number underneath the square root, the radicand, and we're going to divide it by our first prime number. So I can make that list again here if you want to write it down. 2, 3, 5, 7, 11, dot, dot, dot. Okay, so I can divide 24 by 2. 24 divided by 2 is 12. I can divide 12 by 2. That would be 2 times 6. And then I can divide 6 by 2. 2 times 3. 3 is not divisible by 2, but it is divisible by our next prime number 3. So that'd be 3 times 1. And once I get to that 1 on the right side, I stop. Okay, and so we can rewrite that square root of 24 as the square root of all of these prime factors multiplied together. Because 2 times 2 times 2 times 3 gets you right back to 24. So we can rewrite this as the square root of 2 times 2 times 2 times 3. So now, to simplify this, we look for a pair of prime factors. So underneath the square root, we'll see that there is a pair of 2's right here. Okay? When there is a pair, one of them comes out of the radical. Okay? And we don't worry about it anymore. All right? And that's our only pair. So when we rewrite this expression, we're going to bring the 2 outside of the square root. Now, we have numbers that are left over. Those leftover numbers are 2 and 3. And so whatever is left underneath the square root, we just multiply those back. So 2 times 3 is 6. So the square root of 24 simplifies to 2 square root of 6. All right, our next problem, we have the square root of 128. So since 128 is even, we can start by dividing by our first prime number, 2. And 128 divided by 2 is 64. And then we'll be able to divide by 2 again. So that would be 2 times 32. 32 is also divisible by 2, so that's 2 and 16. 2 times 16 gives you back to 32. 16 is divisible by 2. 16 divided by 2 is 8. And then 8 is divisible by 2. That's 2 times 4. And 4 is divisible by 2. That's 2 times 2. Lots of 2's here. And then our last one, 2 is divisible by 2. That is 2 times 1. And we stop there. Okay? So 128 can be rewritten as 2 times 2 times 2 times 2 times 2 times 2 times 2. So 7 2's multiplied to itself. Okay? So I'm going to rewrite this as 2 times 2 times 2 times 2 times 2 times 2 times 2. Okay, so surely, because we have a bunch of 2's, we will have some pairs of 2's. So I have 1, 2, 3 pairs of 2's. And for each pair, 1 2 goes out of the square root. Okay, and if you remember, we said anything outside the square root, we just multiply all those together. So when I write my final answer, I'd have to take this 2 times 2 times 2, which is 8. And then that leftover 2 stays inside the square root. So 8 square root of 2 would be my final answer. All right, moving on. So our next one we have is the square root of 54. So just like the others, we're going to start it by first dividing by 2 because it's even. So that would be 2 times 27. Now 27 is not divisible by 2, so you go to your next prime number, which is 3. So this would be 3 times 9, gets you back to 27. Then we can divide 9 by 3. That's 3 times 3. And then 3 is divisible by 3. 3 divided by 3 is 1. And we're done. So we are going to rewrite the square root of 54 with our prime factors on the left side here. So this would be the square root of 2 times 3 times 3 times 3. And once we've rewritten it like this, we're looking for any pairs of prime numbers. In this case, I only see one pair, and that is a pair of 3s. So that means one pair, or 1 3, goes out of the radical. Okay, there's nothing else outside the radical, so we just have that 1 3 out here. And then inside the radical, we're left with a 2 and 3. So whatever's left over, we multiply those. 2 times 3, which is 6. All right, so let's look at our next one. This time we have negative 2 times the square root of 75. So this one, we just have to be careful that we don't forget about the number outside of the square root. But we're still going to start it the same way. So I take 75 and I want to divide it by the smallest prime number possible. So if I start with 2, this is an odd number, so 2 does not divide into 75. So I go to our next one, 3. And 3 will, because 75 divided by 3 is 25. But now 25 can't be divided by 3, so I move on to the next prime number, which is 5. And that is divisible by 5, so 5 times 5 gets you back to 25. And then, of course, this 5 here is also divisible by 5. And I'm left with the 1 on the right, so that means I'm done. So I'm going to rewrite this with 3 times 5 in the square root, or underneath it. So when I rewrite this, I want to make sure I don't forget about that negative 2 on the outside. Square root of 3 times 5 times 5. So we look underneath the square root, and there is a pair of prime numbers. You have a pair of 5s. So that means 1 5 goes out of the square root. And whatever's outside the square root, we multiply. And since we started with the number outside the square root, this negative 2, we want to multiply negative 2 and 5 together. So that's going to give me negative 10. And then we're left still with that 3 underneath the square root. So we'll have negative 10 square root of 3. And that is our simplified answer. All right, we got 2 more. So this is, next one we have 2 square root of 18. Again, we have a number on the outside that we don't want to forget. Okay, so square root of 18. So when we do our factor tree, our first prime number 2 would divide evenly into 18 because that's 2 times 9. 2 does not divide evenly into 9, so we go to our next one, 3. So 9 divided by 3 is 3. 3 can be divided by 3 because 3 divided by 3 is 1. So we got to our 1, so we stop. So I'm going to rewrite this with our 3 prime factors we got. Okay, so this would equal 2 square root of 2 times 3 times 3. Okay, so when we look underneath the square root, there is a pair of prime numbers. We have a 3. So that means we bring out a 3 from the square root, from underneath. And when we write this, we're going to take the 3 we took out and multiply it by the 2 that was already outside the square root. So 3 times 2 is 6. And you'll see that we have a 2 left in the square root, or left underneath it. So we keep that in the square root. And here's our answer. All right, this is our last one. We have -3 square root of 42. So when I start with this one, I can divide it by 2, our first prime number, because 42 is even. So that would be 2 times 21. 21 is not divisible by 2, but it is divisible by 3. So that would be 3 times 7 gets you back to 21. Now 7 is not divisible by 3. So you go to your next prime number, that's 5. 7 is not divisible by 5. So you go to the next one, which is 7. And 7 can be divided by itself, so that would be 7 times 1, and we stop. So we're going to rewrite our expression here with those 3 prime factors. Okay, so this will be -3 square root of 2 times 3 times 7. You remember we can write it like this because 2 times 3 times 7 is 42. Okay. Now, when we look underneath our square root here, you'll notice there are no pairs, right? There's no pairs of prime numbers. So what that tells us is this problem was actually already fully simplified. Okay. So -3 square root of 42 was its simplest form. So your assignment today will just be a lot of this simplifying square root, simplifying radicals, and then there will be a little bit of review of previous topics on the back page like normal. So you will be working on that, and I want you to turn in this paper at the end of the period.